So chapter 4 and 11 are done in a bit of a package deal. So we're going to start with a little bit of a review of what we've done so far in chapter 4, and they're definitely not side by side in the textbook. So there is a little bit of linking that's meant to happen here. What I'm hoping to do through chapter 4 and 11 is give you a basic understanding of atomic theory, and then chapter 11 moves into that modern atomic theory. So we've gone through a little bit of stuff so far, so let's just start with a simple recap from chapter 4. So we know that atoms are the smallest unit of matter that retains the properties of a particular substance. So that's what we were talking about with the elements. Elements on the periodic table, most of them can be found in atomic units. And so atoms can bind in fixed ratios to make compounds. And so these are examples of compounds, and the nomenclature, the way of writing this is specific. So this tells me there are 6 oxygen, there are 12 hydrogen, and there are 6 carbon atoms in that molecule of carbohydrate, and you don't need to know that's carbohydrate. So in this one, if I list through in water, that means there are 2 hydrogens and 1 oxygen. Doesn't matter how you list them. The idea here is this is how many of each individual kind of atom. We also had this in chapter 4 where we had a unit in our compound here. And so what happens there is the 2 is distributed because we have 2 groups of this unit here. And so for nitrogen, we would have 2 atoms. For hydrogen, we had 8 atoms. For sulfur, we'd have 1. Whoops, sorry, that's not a 1. A 1. Whoops. And then for oxygen, we'd have the 4. And so oxygen, we'd have 4. And this distribution here, it was kind of a tricky thing. So when we talked about atoms and elements and compounds, we then moved on to atomic structure. And the lowdown that we had was basically we talked about how there were 3 subatomic particles that we were going to care about. We had the protons and neutrons, both in the nucleus. These have very sensible names, that the pros are positive, the neutrons are neutral, so no charge. And the significance of these is that the proton gave the atomic number. It's the location on the periodic table, and it does not change. So that fixes the identity of the atom that we're looking at. Neutrons, in a perfect world, they're the same number as the protons, but there are variations in atomic structure. So if we have a variant in number of neutrons, we call those the different isotope, or the different forms of the different elements. So in the case of carbon, we'd have carbon 12, but we also had isotopes of, say, carbon 14. So the mass number was different. We know that these added together is the mass number. The electrons, and that's where we're going to talk a lot about today. We talked about how they are outside the nucleus. I said that they are actually negative, so the naming would be better if they were called negatrons, but they're not. They're outside the nucleus, and those negative particles are orbiting the nucleus. The cloud is large in volume, but low in mass and density. So up here, this is the dense part in the nucleus, right? The significance of electrons is that that is what gives the chemical characteristics, the chemical reactivity of the elements. And so ions are important because that's an atom becomes an ion when it loses or gains electrons. And so we could have losing electrons would give you a positive charge, or gaining electrons gives you a negative charge when we're talking about ions forming from atoms. So the difference between atomic mass, atomic number, or mass number, sorry, and atomic number, they all sound pretty similar, and this is a good place. So we started off actually with atomic number. That's the number of protons. It's the location on the periodic table. The mass number is the number of protons plus the number of neutrons, and so you might have a different mass number for different isotopes, and those are different for specific atoms. And then mass number, the one on the periodic table, is actually the weighted average. Whoops, I did that backwards. my goodness, I'm not reading the instructions here. Sorry, let's do that backwards. So atomic mass is the weighted average. I'm sure somebody was yelling at me in the video. Sorry, mass number is the number of protons and the number of neutrons. And the atomic mass is on the periodic table. It's that weighted average. So it's the weighted average of all the different isotopes that are present. The last little bit here, and something to remember, is that, yeah, most atoms are elements, but some elements are diatomic. So there's actually two atoms, and we remember them, or I remember them, as the gang that causes trouble, and they're called the Hofbrinkels. So that's all the symbols for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And these all like to hang out as two atoms in a molecule. So they were the exception, that not all molecules are compounds. And so they are a pain in the butt, and we'll try and keep coming back to them. You'll notice some images in your formula sheets. And like I say, I'll keep trying to remind us of the Hofbrinkels because they like to cause trouble. Usually. So moving on in chapter 11, what we're really going to focus on is the arrangement of electrons. And so only electrons are involved in the chemical activity, and it predicts its reactivity, so whether it will react with other elements. There is a lot of specificity in this, and we're going to start with a very simplified structure of how things go. And so we're going to talk about electron orbits as being different energy levels. So this is in the electron cloud where the electrons are orbiting, or how far away they are from the nucleus. And we're going to talk about valence electrons. And valence electrons are the outermost electrons. And so we'll talk about how electrons are distributed with these different energy levels, and try and understand a little bit about ion formation and bonding that we kind of get to after this. So we're going to start out with Bohr model diagrams. There are more of these in chapter 12, but they are a good place to start. So when we start off with this, we're going to imagine these orbits of the electron cloud. And in the first orbit, you could fill up that orbit, that electron energy orbit, with 2 electrons. And so depending how many electrons there are to place, there'll be the same number of electrons as the number of protons, unless it becomes an ion, right, as an element. And so we can place them with this idea. The first shell will be full after 2 electrons are placed. The next shell can hold up to 8 electrons. Now it doesn't have to hold 8, but it could hold up to 8. And so we could see that, say, lithium as atomic number 3, we would have 3 electrons to place. So the first 2 fill up the first energy level, and the next one is stuck on the outside. We would say that lithium has 1 valence electrons. We can go across and take a look at all of these. We could build them all up slowly, but you'll see that beryllium has 2, boron has 3, carbon has 4, and on up. Fluorine, if we were to talk about how many valence electrons it has, there would be 7 electrons here. And so we were introduced to the periodic table a little bit in the names of all these families. So we have the first and the second. We have the 8th over here with the noble gases and the halogens, and then those transition metals in the middle. And so if we were to take a look at the number of valence electrons down the group or down the family, we could see that all of them in this first column are going to have 1 valence electron. Everything down here is going to have 2 valence electrons. Everything in the third column is going to have 3 valence electrons. And we're only doing this for the first 18 or so here, because things get weird, and we'll build it up. So if I take a look at the 4th group, I have 4 valence electrons. It might be worth almost to start with these noble gases over here, group 8, and see what's going on with them. So how many electrons do they have? They have a full shell. So we could say that they have no or 8, or we could just say full shell. Maybe that's the most accurate, because I wouldn't say that helium has 8, right? And on down the line, you can kind of fill all this in. There's going to be 5 valence electrons in the 5th column, 6, and 7. And so this makes a lot of sense, and it allows us to conceptualize sort of where these electrons are, because that's what's involved in that chemical reactivity. And so if we were to kind of make these into people, or talk about them in terms of like personal traits or human traits, there's sort of an innate desire for all of these atoms to have a full set. So there's an urge to be stable. There's an urge to have a full valence shell. And so it might change depending which element we're looking at, but generally in these two rows across here, we're looking to have 8. Now, it can kind of attain this full valence shell in a few ways. When it attains a full valence shell, it's going to either lose electrons or gain electrons. We talked about how losing electrons makes things positive, and remember, cations are positive and gaining electrons are the anions, right? And so these ions are those charged particles that result to achieve that full valence shell, to make these atoms happy. So that loss or gain of electrons happens to make a complete valence shell, and the noble gases aren't reactive because they already have a full valence shell. They're already happy on their own. They don't need something else to complete them. They don't need to give up an electron to be happy or take an electron to be happy. They're happy just all by themselves. So drawing these Lewis dot structures, we're going to come back to it in the next chapter, but they are a useful bit to kind of build your understanding of atomic structure. As we are going to learn, there are some problems with the Lewis dot structure, and it's kind of in that they're maybe a little overly simplistic, but they're a good place to start. So we generally write down this symbol and determine the number of valence electrons. And we can do that by either filling and counting or by inferring information from the periodic table. Maybe which column these things are in, or which common ion is formed. And so that's where having that common ion formed is useful. So we can either count or use common ion formed. And we talked about that in chapter 4 with the combining capacity. I think that's the way your periodic table talks about it. So let's try these ones. So boron, if I were to kind of draw this out and count it, boron would be atomic number 5. And so I would have 5 electrons. That would be the nucleus. And the first shell would have 2 electrons in it. And then I would have 3 to place. You generally go for the 12, the 3, the 6, and the 9 in whatever order, and spread them out as much as you can. And so in this one, if I do, this isn't really the Lewis dot structure. The Lewis dot structure would be write down the symbol, and then we only concern ourselves with the valence electron. So I'd have 3 valence electrons to place, and you can put them on really any old side if I copy what I've done here. Right? Predicting the formula for each of the elements. If we were to talk about this and then take it to the next, for the ion formed, this one is going to lose 3 electrons to be full and become the boron 3+ ion. And so by seeing these Lewis dot structures, it gives you a way to see how that ion is formed, because that's the way that boron's going to become happy. Phosphorus, we could take a look at it in a number of different ways. I'm going to start by building it out and counting it. So phosphorus on the periodic table, I'm looking at my key and it's still not helping me, would have 15 electrons to place. And so this would take a long, long time. So there'd be 2 and then 8 more, so we're up to 10. And then I would have 5 more to place in this valence shell, right? There's 4 and 5. You start again at the 12, the 3, the 6, and the 9, and then start doubling them up to get to that full outside shell. So doing it as a Lewis dot structure, again, this is just my counting, right? And so I'd have a phosphorus, a P in the middle, and I would have 5 valence shells around my symbol. And maybe it's worth looking at the periodic table, but the easiest way for this to become full is to gain 3 electrons. And so when it does this, if it gained 3 electrons, it would form the ion of P3-, or phosphorus 3- charge. You can cross-reference with your periodic table and see that that is the common ion formed on your periodic table. So two more doing this laborious way of counting them all out. There's so many ways of using your periodic table. So oxygen, atomic number 8 would have 8 electrons to place. So I'd have 6 valence shells or valence electrons in my outermost shell. And so the Lewis dot structure would have 6 electrons around it. And the easiest way for this to become happy or full is to gain 2 electrons. It wouldn't lose all 6. It would be much easier to gain the 2. And so oxygen becomes oxygen 2 minus as the ion. The last one, fluorine, and maybe with fluorine you're ready to be like, okay, I listened to what you said about group 6 and group 5 and that kind of thing. So fluorine, we have a nucleus, and then being atomic number 9, I would have 2 electrons in the first shell and then 7 in the next shell. I'm missing 1 electron here. So the Lewis dot structure of it would be fluorine with the 7 valence electrons. And the easiest way for it to be happy would be to gain 1 electron to become fluorine minus, or fluorine 1 minus as the ion. It can be either just the minus or the 1 that is understood to be in there. So let's take a look at the next ones down here. These ones you could count up. You can also work a little bit backwards. So the Lewis dot structure for potassium, if I draw it, if I find it on the periodic table, I can see that it's in the alkali metals. It's in the first column. All of those are going to form a positive 1 ion, or have the combining capacity of 1 plus. It has that because it has, 1 valence electron. I got carried away. So if it loses that 1 electron, it will become the potassium ion. Argon, if I were to draw argon out, there is no ion formed because argon is a noble gas and it already has a full shell and it can't lose or gain to become the ion. Aluminum, and so aluminum, sometimes it's easier, especially with these metals that are in the middle. So finding aluminum on the periodic table, I could see that the common ion formed by aluminum is 3 plus. So it might be worth kind of working it backwards. So you have this information on your periodic table. Well, if it has an ion formed of 3 plus, that means it's going to get there by losing 3 electrons. And carbon, again, you can do this in a number of ways. You could see which group it's in, right? It's in the 4th group. And so that means it has 4 valence electrons. You could also talk about the common ion formed. It says that it's going to be carbon 4 plus. And so to do that, that means that it's going to lose 4 electrons. Sometimes it's even harder to predict. Again, on these ones, you could use a periodic table for any of them, but some of them you're really forced to. So if they're not in those groups that we talked about before, right, they're in the transition metals in the middle, sometimes things get weird. And so it's worth taking a look at the common ion formed and kind of work backwards. So zinc's common ion is zinc 2 plus, and it gets there by losing 2 electrons. So it loses 2 electrons. Well, it has then 2 valence electrons. I did them on the sides of my key, but whatever. 2 valence electrons. Tungsten in this one, if I were to take a look at tungsten on my periodic table, it has 6 plus as its common ion formed. And so at this point, with this overly simplistic way, which is actually not super accurate, as we're going to see in the coming sections, we should have 6 valence electrons in order to lose 6, which seems weird, counterintuitive. These are not really accurate. They illustrate the problem with the Lewis dot structures in that our electron arrangements are actually more complicated than we're starting off with here. So we lose 6 electrons. Copper If we take a look at copper on the periodic table, it's number 29 if you're having a hard time finding these things. Tungsten is number 74. It might be worth using that alphabetical chart. Copper could actually form two different electrons. And so what we're led to believe here, I'm going to fill them out. We have copper plus and copper 2 plus. It has multiple combining capacities, and clearly our Lewis dot structures are not giving us a clear image to figure out how this is possible. So we could have copper losing one electron in order to form that 1 plus, right? So it could lose one, or maybe it's losing 2 electrons. And so with these ones, this is sort of the illustration that we've got a problem. Electron arrangement is more complicated than the Lewis dot structures are going to allow us to understand. I think they're a decent place to start, and I will come back to them as we talk about other things through the course, because I think they're a good way to conceptualize this. So if Lewis dot structures and this orbit arrangement is letting us down, we need to move on in our understanding of what's going on. And so in the next page of your notes, you'll find a really nice sort of infographic of the history of the atom. So last time we talked about Dalton and how he started out with a theory of atomic structure. And he was right on a lot of things, but there were some fixes to his works. We talked about Thomson and Thomson with the plum pudding model or the chocolate chip model, where they knew there were negatively charged particles and surmised there had to be something positive in order to hold all that together. And so they figured it was the dough of the cookie or the pudding of the plum pudding. Moving on to Rutherford and the gold foil experiment, where he shot particles, positively charged particles, at a very, very thin layer of gold. He found that it didn't go straight through, that it was actually, the particles were ricocheting off of something that was very dense, and he assumed positively charged, which we know now are the protons in the nucleus of the atom. So Bohr and these Lewis dot structures are kind of where we're at next, and we're going to move into quantum model, or the modern theory, with Schrodinger in this chapter 11. So these are kind of where we have left to go. And this is where we've already been so far. So let's carry on with Niels Bohr and his understanding of atomic structure. So we've got this idea that electrons are somewhere outside of the nucleus, and really understanding where we started off with that understanding of orbits and electron arrangement. Let's move on to the Bohr model, and then we'll take a break where we stop talking about orbits and start talking about orbitals. So Bohr is a stepping stone, and the key thing about his work is that he basically found a way to illustrate that the electrons outside of the nucleus of an atom have different energy levels. And so this fits with our idea of orbits, right? He illustrated this because when he could energize an atom, he could actually make the electron jump to a higher energy level. When the electron came back down, it released that energy that it had in the form of light. And so this made it visible. It made it possible for us to actually make a map of electron energy levels. And so each jump would give off a different amount of energy that corresponded to a different wavelength or color. And so we know on the electromagnetic spectrum, right, like the spectrum of light, light can be separated into the colors, like colors of the rainbow, the stuff you already know about, right? And so when he energized a hydrogen, he found that he could kind of map out these different energy levels, and N is the different number for those energy levels. And so he could kind of figure out these different sort of energy levels and try and understand where the electrons were around the nucleus in something more than the Lewis dot structures. So these orbits, like he talked, were kind of planetary. And so they were a different, like planets around the sun, right? That's what it said in that infographic. And so this would be N1, N2, N3, right? And so he could kind of map these sort of steps that the energy, that the electrons could jump up for. And so in these ones, it was really cool. The problem with it is that it only worked for hydrogen. And so basically we're going to continue our story with the wave mechanical model and a bit on the Schrodinger and quantum mechanics in this next little bit. And again, with these, we're talking about orbits here. In the next part of this chapter, we're going to start talking about orbitals. And it doesn't sound like a big difference, but it makes all the difference in our understanding of how atomic structure is understood today.